Everybody, welcome back. We didn't just have a little get together for a couple minutes. We're totally starting afresh. So we're gonna pick up Latin next time. This time, no headache today. So let's go ahead and get into it. We were talking last time about the complex fractions, i.e., fractions within fractions. And just as a reminder of our terminology, there's the big numerator and the big denominator, and then there's the small denominators and small numerators and stuff. So there is the old-fashioned way to simplify these things, which would be to get it to be something like this format right here, because then you can just, it's a fraction over fraction, you flip and multiply. That is one way, and it will work 100% of the time. However, it's not as fast as this other method that kind of relies on what we did with rational equations, where you multiply the entire thing by the LCD of everything. Because if I do that, I can do this because this is cleverly multiplying by 1. It doesn't change anything. And so if I think about that, then I can apply this entire thing to the big numerator and this entire thing to the big denominator and cancel out all of the fractions that are there. Therefore, I still just have one main fraction bar and I've gotten rid of all of the other small fractions. So let's go ahead and do an example here. 1 minus 1 over x minus 56 over x squared over 1 minus 64 over x squared. So the LCD of everything would just be x squared. So you could put this off on the side. LCD is equal to x squared. So what I'm going to do is I'm going to multiply the big fraction by x squared over x squared. Yes.
Now, why is it not x squared?
Excellent question. Excellent question. Why isn't it x squared? Because it's all like, so the LCD is always going to, thank you for bringing this up. This is a good reminder of things. The LCD is always going to be, where is it? Where are we?
Oh,
no. All the factors that you see raised to the highest power that's amongst them. So in particular with this one right here, there is an x. They both have an x, but one of them is being raised to the second power. So that's the highest power of x that we see.
So if it was like
If
1 over x minus 2 minus 56 over x squared, then would be x minus 2 over x squared?
yes. So if this was x minus 2 here, let me make that way better. It's hard to read. If this had instead been, if right there had been x minus 2, and let's just say this is an x now, then it would be x squared times x minus 2. Because there is a power, like there's a factor of x, and the highest power of x that I see is an x to the second power, and then there's that factor of x minus 2.
I think that's what I was making a mistake of.
Were you multiplying by extra stuff? Probably.
X by x squared.
Gotcha. Yeah, that like it will work in the the long run, but it will take a lot longer and there's more room for error.
That wasn't good right answers.
For sure. So now that we've got this, we're going to distribute this into all three pieces of the big numerator, and we're going to also distribute it into all three pieces or all two pieces of the big denominator. When I distribute it into the big numerator, the 1 times x squared, that's just x squared. The 1 over x times x squared, that be one of the x's cancels, and this becomes minus x. And then on the third term, the x squareds completely cancel. So it's x squared minus x minus 56, all divided by. And then in the big denominator, 1 times x squared, that's x squared. And then 64 over x squared times x squared, the x squareds cancel, and we've got that. And then that will factor nicely, just to save us on time. But if I encourage you to check it on your own, is to factor this. This will factor to x minus 8 times x minus 7, or sorry, x plus 7, divided by x plus 8 times x minus 8. And the x minus 8s cancel, leading to a final answer of x plus 7 over x plus 8. Yes.
Does it typically happen, except like I noticed yesterday, like I would usually do the bottom, like the denominator odd factor, simplify that first. Because it seemed like every time, whatever, if like when it's gonna be 8 plus or x plus 8 and x minus 8,
Mhm.
like it seemed like the top, when you factor, it always would have at least one of those, like factor to make it easier. Is that usually true?
Usually, more often than not, yes. Like that's the like that is the student in me speaking, not the teacher. The teacher is saying like, well, you shouldn't just assume blah 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 blah.
It just seemed like it made it way faster to factor.
You're just assuming from the context.
Yes, assuming from the context. There, like that actually brings up a very, very good point. Something that you'll see a lot in calculus, actually, if you plan on taking it, is you'll see instead of this, you'll see something like this: limit as x approaches 8 of x squared minus x minus 56 over x squared minus 64. So this is a limit, which is something you'll see in calculus. And not, as a teacher, I always tell you should check your like you should plug it in to see if it's a problem or not. But as a student, if it's given like that, it's 9 times out of 10, it means that this, when you like at x equals 8 will equal 0. So you know that x minus 8 is a factor. So you can immediately start factoring it right off the get-go.
Yeah.
So that's actually something I spend like a good solid 20 minutes on with my classes in calculus, just reminding them, hey, you're going to plug it in anyways. If it equals 0, then by the factor rule that we learned in 126, that means that you could just write x minus 8, and you don't even need to worry about like really testing, like using rational zeros theorem or AC method or anything like that. You can just say, okay, one of them has got to be x minus 8, and then fill in the rest of the blank by just some factorization. So, any other questions? But yes, you can usually assume and see what happens.
It was just during Alex when I was getting like
Oh,
tired of factor, and I was like, it seems like this is working. Makes it a little easier.
exactly right. So yeah, factor the bottom one first, like factor the easy one first, and then if you don't want to sit down and do the AC method, absolutely just sit down and assume, well, what if it was x plus 8 and see what happens. This next one. So would you guys like to see the alternate method to see if you like it more? Okay, so the alternate method would be to simplify the numerator, the big numerator, and simplify the big denominator first. So in the big numerator, I need to combine these two things. Like, so I'll put alternate approach.
That's what Alex was having.
Yes. So this the 7 is missing an x plus 3 over an is missing a denominator of x plus 3. So I'll multiply it by what it's missing. And then the similar thing for the denominator here, I'll multiply the 4 by what it's missing, like its common denominator, which would also be x plus 3. And doing so will give me 7x plus 21 plus 14 over x plus 3 all over. That was the big numerator. Now the big fraction bar, and then the big denominator will now be 8 plus 4x plus 12 over x plus 3. And so we'll simplify. Does anybody have any questions on where anything came from, like the 7x plus 21 or the 4x plus 12? It's coming from the distribution, just in case you don't want to ask the question. 7 gets distributed in here. That's why it's 7x plus 21. And then by multiplying this one in blue, I've ensured that the two terms in the numerator, in the big numerator, have this common denominator, so they can be combined. Same thing for the denominator. By multiplying by what I did in green, I have ensured that the big denominator terms all have the same denominator, the same small denominator. And so that's why I could combine them right off the bat. And I could do certain, like there's plenty of ways you can do the algebra to simplify it yourself. I'm going to rewrite this now as 7x plus 35 all divided by x plus 3 all divided by 4x plus 20 over x plus 3. But if you want to skip that step and go immediately to flipping and multiplying at the same time, that's your call. But now that it's a fraction over a fraction, we know how to work with that. That's division. So division by a fraction means you flip and multiply. So this becomes, and I'm going to factor it as I'm going through it because I noticed that the small numerator of the big numerator. So in the big top part, the numerator of the big numerator has a common factor of 7. That becomes 7 times x plus 5 over x plus 3. And then the big denominator, since I'm dividing by it, I'm going to flip and multiply. So it becomes x plus 3 over, and I'm going to factor out a 4 from the 4x plus 20 and get x plus 5 again. And then the x plus 3's cancel, and the x plus 5's cancel, leading us to a final answer of 7/4. So if you like this method better, that is fine. It is completely valid to do it this way. I would say that in practice, it seems more intuitive. It's exactly what we have been doing. It's not a new method, but it takes a little bit longer. If we have time, I could show like the other method is going to be a lot faster. But you're saving, like, I guess at the end of the day, you're saving yourself maybe 30 seconds. So if you really like, if it makes sense and you can master that one, go ahead and do it. Otherwise, this method is completely valid. But yes.
What's the, like, where are the differences of both? Because like, if you were multiplying all of them by like the denominator, like the LCD, wouldn't you still just be getting 14 anyways?
So what it would do, I would still get 7/4. Let's go ahead, actually.
Like over x plus 3, like, is it just because you mean you're not writing that times the LCD again? Like that's what's saving you time?
Yeah, you're not writing like so. By doing that, it makes it so that you no longer like by multiplying the entire big numerator by the LCD of everything, it will cancel out all the fractions. So all the fractions in the big numerator will be gone. All the fractions in the big denominator will be gone. So you don't need to do any more out. Like all you need to do is simplify that expression instead of having to like. So I appreciate you asking that because it's finally allowing me to put it into words. Is that the difference is if you do it the way that I originally taught, then it will bypass having to do any other calculations other than factoring and canceling. So if you do the method that's the original method that I've taught, the one that we did in part A, then there is nothing else that needs to be done besides just combining things and then factoring and canceling. Whereas if you do it the way that we did it in part B, you have to get it all over one roof, which it does the same thing, but then you also have to do the additional step of divide and flip and multiplying. So there's one extra step. Doing the other method bypasses that. Great question. So this one right here, I'm going to do it the main method again. And this is the other reason why is especially when it comes to calculus, you start having to write some pretty nasty, really long things. And I always encourage, like, if you can save some space, this problem, when I give it to my students in calculus, this problem right here, it can take about a half a page, but we're about to compute this in no time at all. So if you want to do it with the method that I've taught beforehand, like not the method that we just did in part B, then the LCD of everything, the denominator doesn't have an LCD. It's just an H. So its denominator is 1. So the LCD of all the terms is just the two denominators from the big numerator, the 2x plus 2h minus 5 and the 2x minus 5. And so when I do that, when I distribute it into the top, what's going to happen is for the first distribution, the 2x plus 2h minus 5s will cancel. Oh God, this, oh yeah, no, that's going to be fine. And so we'll get x plus h plus 1 times 2x minus 5. And from the second thing, I'll get minus and then x plus 1. And when I distribute it into the second set, the 2x minus 5s will cancel, and I'll just have a 2x plus 2h minus 5 left. But in the denominator, I'll have an h times a 2x plus 2h minus 5 times a 2x minus 5. Take a second. And I know this is going to be a little tedious, but it's good algebra practice. We're going to need to know it. Like it's good on our algebra skills to go through this. Yeah, JT.
Why isn't it h, 2x8 plus 8 blah, 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 over that same thing without the h?
In like in the big denominator or like here. So right here. Why isn't there a numerator? Because there was no denominator to begin with. So this is getting multiplied directly. Yes, and that's being multiplied into the entire thing here. So it's on the same level as the h. That's the big problem to understand with this method is that this is the main division bar that corresponds to right here. So when I'm multiplying these two like these two things together and these two things together. Yes, JT.
Okay, this might be a dumb question, but like if I were to have done this, I would have because I would have thought that LCD would have been just the 2x plus 2h minus 5.
Mhm.
How come you have to add the 2x minus 5 if like that is in the first equation too?
So it like because it's right here. So it's because it's not the same thing. It's a completely different denominator. So like, and I'm glad you bring that up. It's these are completely different denominators. They look very, very similar, but there's one minor difference, but that makes all the difference at the end of the day. They are two completely separate things. It's just like another example of like to maybe drive that home. It's if I have x squared plus 2x minus 5, and let's just say this is 7 minus 1 over 2x minus 5, they're completely different, right? It's because it has that extra x squared. In the other one, we have an additional 2h that changes it and makes it different. Cool?
Yeah.
Excellent question. All right. And so we'll have to do a little bit of foiling. We'll have to do a little bit of distribution. Did I really make it this annoying? Okay. So that's going to be 2x squared. So however you want to do it, I'm going to distribute the like these three terms into the 2x minus 5. So please watch for just a second. Remember that it doesn't matter, like because multiplication is commutative, it doesn't matter which one you multiply into which one. So you could either do this, you could distribute the x in, the h in, and the 1 in, or you could do it in reverse. You could take the 2 and distribute it into all three things and take the 5 and distribute it into all three things. Either way is fine. It's just your call. Just because I like to do things left to right, I'm going to do it the other way. So I'm going to do x squared, x getting distributed in gives me 2x squared minus 5x. And then plus 2xh minus 5h plus 2x minus 5. Minus in parentheses. I distribute the x in, so it'll be 2x squared plus 2xh minus 5x plus 2x plus 2h minus 5, all divided by h times 2x plus 2h minus 5 times 2x minus 5. A lot of numbers, a lot of variables and stuff. It's intimidating, absolutely. But do not lose heart. It's just trying to scare you. It's just trying to scare you by saying it has a bunch of words in it. It's trying to intimidate you by having multiple things, but don't let it. Any questions so far? Yes.
How come you didn't distribute the bottom at the same time?
Why didn't I foil it all out? For the same reason that I don't do it in the other ones, is it might end up being that once we've simplified it, that the numerator can factor,
Okay.
and so things could cancel. And this is actually something that's going to play a part later on in calculus, that you actually don't even want to do that. It'll save you time in the long run, is to not worry about it. All right. So remember that minus sign is going to get distributed into all the pieces. A lot of pieces. But I'm going to try and skip a few steps here if we're okay with this. So if you're looking at this, we're going to minus a 2x squared. Well, that means that's going to cancel that 2x squared. Isn't that nice? That's convenient. And then you're going to get a minus a 2xh with a plus 2xh. Those are going to cancel. Isn't that nice? And then you're going to get a minus a negative 5x. That's really adding 5x. And that's going to cancel out with this negative 5x. Isn't that nice? And then you're going to distribute this minus sign into the 2x, but you get a plus 2x, and then you get a minus 2x. Isn't that nice? Huh. That's fun. Why isn't that? Something's weird now. Something's not looking right. Because it shouldn't be a 3h. Why is... It'll be a negative 7h, but it shouldn't be. It should just be a... It should just be an... What did I do wrong here? Sorry, give me 1 second. That is not nice. No, indeed, that is not nice. What did I do weird? Wait. Sorry. 1 second. I'm just gonna have to verify something to myself. So fx is x plus 1 over 2x minus 5. So f prime will be 1 times 2x minus 5 minus 1 times x. No. 2 times x plus 1 or 2x minus 5 squared. 2x minus 5. Okay, no, it's gonna be fine. It's gonna be fine. All right. Okay. Never mind. The 2x, the 2h and the 5h are gonna combine, but then those fives are gonna cancel as well. So all that's gonna be left in the numerator is a negative 7h over h times 2x plus 2h minus 5 times 2x minus 5. I think I'm gonna make this one easier next time. I think I'm gonna edit this one and make it a little bit nicer. Well, but I mean, this is good algebra. Negative 7h, yes. Yes. I typically so I'll explain in just a moment. So basically, I mean, you can take an extra step and do all the distributions and then combine like terms, but I promise you all those things will cancel except for the h's, the 5h and the 2h. And then, therefore, the h's cancel. And we get our final answer, which will be negative 7 over 2x plus 2h minus 5 times 2x minus 5. And that is our final answer. And congratulations, you just computed your first derivative. Not even taking calculus tests, and you've already taken a derivative. So, excellent job. And if this looks scary and like you're like, whoa, if that's what calculus is, I want nothing to do with it. This is one part of calculus that you have to get by in order to get to the fast part. Once you pass, like this is about 1 week of calculus, and then after that you kind of skip doing this and you do it the fast way. So this is not a terrible, like this is not what calculus is all the time. Please don't let this intimidate you or scare you away from calculus. Calculus is awesome. It's a very fun course. So any questions on that?
What's the reason you don't do anything to the denominator for the final answer?
Because we don't really need to. Like if it said that it wanted, like, so it said simplify, which really with the way they mean, what we mean is cancel any common factors, combine it, make it into a singular fraction. And as long as there are no common factors that can be canceled, you're good. All right. So that was a little detour that we had to go through to talk about rational expressions so that we can now talk about rational functions. So a lot of the things that we talked about there were preliminary stuff, and just so we know how they all work, but a lot of the things are going to be kind of secondary in the background that we don't need to do too much. All right, so properties of rational functions. So what is a rational function? Well, a rational function is, of course, a function of the form r of x, or let's do f of x, equals p of x over q of x, where p and q are polynomials. So that is to say, something like 1 over x. That is a rational function because 1 is a polynomial and x is a polynomial. 5x minus 4 over x to the fourth plus x minus 2. That's also a polynomial. And then we kind of talked about it before, but it's worth noting is that 1/4 is technically a rational function. Not a very exciting one, but even in itself, by not being exciting, that makes it exciting. There's that paradox in mathematics that I love. We talked about that one, right? The fact that there's no such thing as an uninteresting number. Did we talk about the paradox, like that paradox? Okay, well, there is a fact in mathematics is that there is no such thing as an uninteresting number. And I can prove it to you. But we'll get to that in just a moment. Maybe when we have a break, we'll do that. So the domain of a rational function is all the real numbers except those that would make the denominator equal to 0. That make q of x equal to 0. Which is not surprising. We've already kind of talked about that when it comes to domain. When you're looking for domain of a function, you're always trying to find the places where it doesn't exist to exclude them from the overall set. So we need to make sure that we can't have the original, like the denominator of the rational function being equal to 0. Much like with regular functions and stuff, what's it called? Finding the range is a very, very challenging thing to do algebraically. You usually use that for graphing, but we'll get to that. The x-intercepts are found like normal. So you're going to set y equal to 0. And that is going to say that is solve f of x equal to 0, which means p of x over q of x is equal to 0. Much like normal, you're going to set the y equal to 0 and then solve that equation. Setting y equal to 0, y and the y values and the function are synonymous. F of x and y are synonymous. So by setting y equal to 0, you're setting the function equal to 0. Now, this is why I spent the time talking about the rational equations, is that when we solve this, the good news is it's a very, very quote unquote simple rational equation. It's not like, don't worry, I'm coming right back to it. It's not like this situation here. there is only like either one of these three situations that we were looking at. All three of them had a bunch of different denominators, and we had to find an LCD and all that jazz. But with this situation, there's only one denominator. So in order to solve it, all I need to do is multiply both sides by q of x, which is really only going to which can only happen. So the answer is which can only happen if p of x equals 0. So, and I'm going to put an asterisk, like a star here. So to find x-intercepts, set the numerator equal to 0. We're gonna rehash that one more time. Once everyone's written that down. And explain why. So the main thing, if you're going to find the x-intercepts, you're setting the function equal to 0. That can only happen if the numerator equals 0. If the denominator equals 0, then you're dividing by 0. That's a big problem. We can't do that. The only way this could ever, the only way that f of x could ever equal 0 is if the numerator is 0, right? Because 0 divided by anything is 0, save for 0. 0 divided by 0 is indeterminate. But like the only way that we could solve that is by making the numerator equal to 0. So when we're finding the x-intercept of a rational function, it suffices to just find out where the numerator equals 0. That's what we're going to do. Now, cautionary tale is make sure these x values are in the domain. You'll see an example of this in just a moment in part B of example 2.5.1, why we have to be a little bit cautionary. We need to proceed with caution because there are problems that can arise. Not always, but can arise. And then the y-intercept is found like normal. Set x equal to 0, that is find f of 0. That is find f of 0. That one's not too terrible. So we're going to find the domain and the intercepts of these two functions. So for part A, for the domain, we need x plus 5 to not equal 0, which means that we need x not equal to -5. That's the problem. If the denominator ever equals 0, we don't want to factor and cancel or anything like that. We just want to look at where the denominator equals 0, because even if it's a factor of the numerator, that would mean you get 0 over 0, which, as we've seen, is indeterminate. It's undefined, or it's undeterminable. So if you can see the answer for the domain and interval notation right off the bat, awesome. The answer should be that the domain is parenthesis negative infinity to -5 n parenthesis union parenthesis -5 to positive infinity. Ideally, I'd like you to get to that point in your mathematical career, but at this stage, that's understandable if you can't do that. What I did when I was learning this stuff is I would draw a number line to visualize it for myself. So you got this number line. Here's -5. It has to be plucked out. You cannot equal -5, but everything else is fair game. And so if you're looking at this number line, you can convert that into an interval notation, negative infinity all the way up to -5 with a parenthesis, union the next ray from -5 to positive infinity. But it's your call. If you feel comfortable skipping that step, go right ahead. You can go straight to the domain if you'd like. Then we talk about x-intercepts and y-intercepts. So let's start with x-intercepts. x-intercept. You're setting y equal to 0, which is the same thing as saying setting the function equal to 0, because remember, y and f of x are synonymous. They mean the same thing. So that is to say, we've got 2x squared minus 6 over x plus 5 is equal to 0, which can only happen if 2x squared minus 6 equals 0. The only way that expression could equal 0 is if the numerator equaled 0. And that factors somewhat nicely. There's a common factor of 2. And then it's x squared minus 3 is equal to 0. And so that will factor. That's a difference of squares, as we've learned, right? Anything can be a difference of squares if you want it bad enough. And so this is going to be 2 times x plus the square root of 3 times x minus the square root of 3 equals 0, which gives me the x-intercepts square root 3 and negative square root 3, or plus or minus the square root of 3 comma 0. That the y equal to 0, meaning you're setting the function equal to 0, and that can only happen if the numerator is equal to 0. And I just decided to really make sure we're challenged on the fact that you can factor this even if we don't have nice numbers. Square root 3 is not a quote unquote nice integer number, but that's okay. You can still factor it to x plus the square root of 3 times x minus the square root of 3, which gives us the 2x intercepts, square root 3 and negative square root of 3, which are in the domain. They are in the domain because the only problem that the only thing that causes problems with our function is just -5. Last but not least is the y-intercept. You're going to find f of 0, which would just be 0 minus 6 over 0 plus 5, which is -6/5. So -6/5 or 0 comma -6/5, however you want to do it. Any questions on that one? It's okay if there are. Yes, JT.
For x-intercepts,
Uh-huh.
how can you only put the square root 3, negative square root 3? Like, do you not add the 0 too? Like, you did it for the or, but do you not put it there too?
Oh, good point. So the thing is, that's not there is no x-intercept at 0. That's a point. That's the y coordinate. Why do you think? Because it's not wrong. I'm like, what I wrote is absolutely correct. And the reason for it, if this was 2x, then we'd have a 0, but it's not 2x, it's just 2. So by the 0 product rule, either 2 equals 0, but that's ridiculous, or the square root of x plus 3 equals 0, or x minus the square root of 3 is equal to 0.
I was thinking more, so I guess I was thinking as a 2x basically.
It's, yeah, absolutely. I'm glad, like, I guarantee you we all make that mistake one time in our lifetime, at least once. So the next one. So domain. How would we find the domain? So like, try not to look at, I'm covering it up on my screen and you can't, let me, let's erase this for a second. How would we find domain? So don't think of this as anything new. This isn't anything new. We're like the domain, we've already learned how to do this. Set the denominator equal to 0 because we don't want to be dividing by 0. So for the domain, x squared minus 4 cannot equal 0. That means that x cannot equal 2 and -2. I hope everyone's okay with me skipping a step there and saying that it's going to be 2 and -2. Because x squared minus 4, that's a difference of squares. That'll factor to x plus 2 times x minus 2, which will give me the two issues at 2 and negative 2. So if you were to draw it on a number line, you don't have to do this unless you are having trouble writing the interval notation. But here's 2 and negative 2. Those values have to be plucked out, but everything else is fair game. That is to say that the domain should be parenthesis negative infinity to negative 2 parenthesis union negative 2 to 2 parenthesis union parenthesis 2 to positive infinity and parenthesis. And so you'll note that I didn't bother factoring the numerator at all. And I'll explain why in just a moment. Any questions on the domain? Once again, this is not anything new. It seems like it is because we're in a new section, but it's just because we're talking about what we've already learned in relation to this, how to apply what we've already learned, which is that domain comes from finding out where the function, what values aren't in the domain. And that's going to be trying to avoid places where things don't exist, i.e., we don't want to divide by 0. We don't want to take the square root of negative numbers. We don't want to take the even roots of negative numbers. And then unit 3 will talk about logarithms, and we don't want logarithms to be negative. But that's getting ahead of ourselves. So, x to the domain. Then we'll do the x-intercepts. Now, I could say set y equal to 0, which is correct, but really when it comes to a rational function, all you need to do is set the numerator equal to 0. Setting y equal to 0, which will mean that you're going to set the numerator equal to 0. That is 2x squared plus 4x minus 16 is equal to 0. I needed to, I'm going to give more space next time. There's not enough space to do these things. So just in the interest of time and the interest of space, I'm going to factor it for us right off the get-go. This will factor to 2 times x. Plus 4 minus 2, yes. Equals 0. Yeah, because you get 4x minus 2. Yeah, yep. And so that gives me x equals negative 4 and positive 2. However, positive 2 is not in the domain. So x-intercepts are 4 only. And you don't need to write the only thing. It's just my way of telling you that there was another option, but that option did not work. That's the way I've always decided to try and make sure it's very clear to my students. So if you see that only, whether it come up in a review or on a solution guide or anything like that, when I say 4 only, it means that there were other options, but this was the only one that actually worked. So that is our x-intercept. And then for y-intercepts, r of 0 will just be 0 plus 0 minus 16 over 0 minus 4, which is going to be 4. Because it'll be 16 over 4, which is, oh, negative 4 only, negative 4. I'm sorry, I missed the negative sign. I wrote it in the original part, but I didn't write it there. So 4 or 0 comma 4, depending on whether or not you need to write it as an ordered pair or not. Okay. Any questions on that? Okay. let's take a break. I think this is a good time, it's a good enough time as any to take a break because we're going to be starting to talk about asymptotes in just a moment. So let's come back together at 10:05 and we'll pick it up then. People go watch the recording, do some guided meditation or email your congressperson. Welcome back, and we'll talk about the next thing about rational functions, which is a new concept that we haven't really seen before. We've heard of domain, we've heard of intercepts, but asymptotes. Not the P is silent like in pterodactyl. It's not an asymptote. It's not an asymptote. It's an asymptote. And what they are very, very unique things. So the unfortunate fact about asymptotes, because we do study rational functions now because they are a very, very natural extension of polynomials, because they are just a polynomial over a polynomial. But asymptotes at their core, they are a calculus definition. They require calculus notation in order to be truly understood, but we don't need that to get by for now. Like we will get by just fine with an intuition. A vertical asymptote, which we will from now on write as a VA because I do not want to write that out. I hate writing out vertical asymptote every time. It's a vertical line. And if we remember from 1.4/5, vertical lines are always of the form x equals a number because a vertical line isn't a function, but it is an equation. It's x equals ASYMPTOTE. But it's a vertical line x equals c that splits the graph locally into pieces. In particular, as your x values get closer and closer to c, you'll see that the function values, the y values, will get infinitely large in either the positive, the up direction, or in the negative or the down direction. That's what a vertical asymptote does, is it splits the graph locally. Whereas a horizontal asymptote, which we will call an HA, because I don't want to write that out, is a horizontal line. And horizontal lines are lines of the form y equals a number. So this is of the form y equals L that describes the end behavior of the function. In particular, as your x values get infinitely large in the positive, the right direction, or in the negative left direction, the function values, your y values, will start to approach L. They'll get closer and closer and closer as time goes on. So I've got a picture, a pictorial representation of this that I think will be a good piece of it. So that dashed red line, I know it's kind of hard to see unless I zoom in. This is your vertical asymptote. This is a VA at x equals c. So this is the value c, and this is the value capital L. And this line right here is an HA at y equals L, capital L. And I wanted to give us a couple two notes on this fact here. So the vertical asymptote is that dashed line that's going up and down, and that horizontal asymptote is that thing that's going left and right. And so, two notes. The first note is that functions, quote unquote, hug their asymptotes. Like, you know how, like, so what I mean by, oh, like, let me zoom out so you can see that. So functions hug their asymptotes. So like, just imagine as you're going into, if you want to give somebody a hug, you get closer and closer until you, I mean, I don't need to describe a hug to you guys. Maybe, I mean, I do for my own sake. My son is not a touchy kid, so he doesn't like hugs. But either way, you know how hugs work. You know, you get closer and closer until you finally embrace. That's the same thing with these ones. You don't act, but this is a very, very strange hug. You don't actually embrace. You don't finally touch each other. You never actually, I mean, you get very, very closer and closer and closer, but you don't really reach it. So they hug their asymptotes. So the main reason that's going to help us when we talk about graphing them. And so when you're graphing them, basically, as you get closer to them, they need to get like as you start drawing your graph, it needs to have the intention of getting closer to the asymptotes one way or another. And the other thing is that since HA's horizontal asymptotes, since they deal with end behavior, a function can cross its HA, but functions cannot cross VAs. That will make sense once we understand how to find them, but the fact of the matter is horizontal asymptotes deal with end behavior. So locally speaking, you can go over them just like I've drawn this picture. This function goes up and over. Oh, let me use a different color so we can see it in action. This function goes up and then over your horizontal asymptote and then levels off and goes back to it. It starts to hug it as we get further and further on to the right.
What did that say?
I don't know why it didn't. But vertical asymptotes are very, very particular. You cannot cross through it. It is on like on both sides of it is one side or the other. Later on in calculus, you can kind of manipulate this definition just a skosh, but at the end of the day, it's still you cannot like there is no way to have a connected graph, a continuous graph, if it will. There's no way for this to magically get connected like that. That doesn't happen because vertical asymptotes have to do with a certain behavior. So you can cross like if you're looking at a graph and you see like, oh, it crossed its asymptote. It probably might have crossed its horizontal, but it cannot cross a vertical. And for our class, for rational functions like these, they will only ever have one horizontal asymptote. You can have at most one. In calculus, you'll start to study functions that are not as nice, and they can have up to two, but you can only have at most two. You can have infinitely many vertical asymptotes. You can have at most two horizontal. So how do we find them? It's great. I've given you a picture, coolio, but how do we actually find these asymptotes? So we'll start with vertical asymptotes. So the procedure for finding vertical asymptotes and also for finding removable discontinuities. So step one is to factor the numerator and the denominator completely and cancel any common factors. If a factor gets completely canceled out, there will be a hole in the graph where that factor equals 0, called a removable discontinuity. And this is going to seem weird. We will talk about what they are and how they work in just a moment. But let's talk about the procedure first, and then we'll explain why it is the case. So in this example here, f of x will equal 2x squared plus 6x divided by x squared plus 4x plus 3. And that will factor to 2x times x plus 3 over x plus 1 times x plus 3. And so what we'll see here is that x plus 3 will get completely canceled out. Which implies there's a hole at x equals -3. So if a factor gets completely canceled out, like this one did, then there will be a hole in the graph. There will be a little open circle where that factor equals 0. So x plus 3 equaling 0, that gives me a hole at x equals -3. And so writing it in the new format, After canceling, we get 2x over x plus 1. So step one is trying to find if there are any removable discontinuities or holes. In complex analysis, if you become a complex analyst, instead of calling them a removable discontinuity, you get to call them something way cooler. You get to call them a removable singularity, which I think sounds way cooler, right? Singularity. Sounds like we're talking about something like a black hole. So, and that's just because the complex analysts are the coolest people in the math department. It really is true. They walk around like they got stunner shades and all that stuff. They literally are like they go to the meetings late. The meeting doesn't start until they walk in, much like Kesha. The party does not start until they walk in. True story. Okay. So now that we've canceled everything like that, then we can look for vertical asymptotes. A rational function will have vertical asymptotes wherever the new denominator. I'm going to highlight that in pink. Wherever that new, the new denominator. This is the new denominator. I put new in quotation marks though, because more often than not, nothing will cancel. More often than not, when you're tasked with graphing a rational function, you'll factor it and nothing will cancel. That is the goal. That is the hope, is that nothing cancels. That is the nicest case. So I say new denominator because sometimes nothing cancels, and so your new denominator is also your old denominator, but we'll see that in a moment. So you will have vertical asymptotes wherever the new denominator equals 0, and then with regards to the holes in the graph, the y-coordinate, you've already found the x-coordinate of the hole. The hole will happen at x equals -3, but to find the y-coordinate of any removable discontinuities, they'll be found by plugging in that x value into the simplified rational function. So for this one, and don't worry, we are going to explain why all this stuff works and why this works in just a moment. So for the VA, you've got to set x plus 1 equal to 0. That gives us a vertical asymptote at x equals -1. And remember, a vertical asymptote is an equation. It's an equation at the end of the day. So you can't just say that there's a vertical asymptote at -1. If you write on the exam, the vertical asymptote is -1, that's not going to be mathematically valid. That is saying something that's not true, because -1 is a number. X equals -1 is an equation, is a vertical line. So please remember to write that. I will always make sure on exams to write your answer as an equation so that you know to do that. But either way, then there's a hole at x equals -3. Plug in to simplified, which is 2x over x plus 1. So that's going to be 2 times -3 over -3 plus 1, which is going to be -6 over -2, which is +3. So there's a hole at -3, 3. I wrote that very quickly, so we'll recap. I'm realizing we have to go over horizontal asymptotes, we have to go over slant asymptotes, and then we also have to go over graphing. So we are not going to be able to finish this section. We're not going to be able to finish this section today, which means that the homework will be extended until next week. Don't worry about the quiz for this week or the homework for 2.5. Those will be extended until next week to get this all finished. But I'd rather take my time on this one than try and rush it, because it's a rich section. I absolutely love rational functions. They are so cool. They have a lot of fun aspects to them. It's just a cool new Lego design to study. So, in short, You factor everything, cancel any common factors. If anything gets canceled completely, there's going to be a hole where that factor equals 0. And then based on that, anything that didn't get canceled, anything in the denominator that equals 0, that's where you're going to have a vertical asymptote. And the holes will be found by plugging in the x value. Now, first and foremost, let's talk about why vertical. I don't have a description of why vertical asymptotes occur where the denominator equals 0, but I will explain that now, and then we'll talk about discontinuities. So the vertical asymptotes will happen where the graph does not equal 0. Where the denominator equals 0, because that's going to be a place where the function is undefined. And if you have the time, so for this one here, go ahead and try and plug into your calculator, plug in negative 0.9 into this expression. And you'll see you get a very, very large positive or negative number. You plug in, wait, let's see here. You should get, if you plug in negative 0.9, you should get a very, very large negative number. Let's see, let me bust out my calculator. So for all the x values. So 2 times negative 0.9 divided by negative 0.9 plus 1. You get negative 18. But that's just 0.9. That's only that's 0.1 away from negative 1. But if I do 0.99 instead, I get negative 198. So by moving myself 9/10 closer, I now jump up over 180. And then if I put 0.999, so negative 0.999 instead of just 0.99, I get negative 1,998. So it just gets infinitely larger as we get closer and closer to it. And it's because when you get closer and closer, so I think we talked about this, but if we didn't, the smaller your denominator, the bigger the overall number. So if your denominator is less than 1, it gets larger and larger. Case in point, to look at this, if I have 5 divided by 0.5, if I divide by a number that's smaller than 1, that actually makes the whole thing larger, right? So if 0.5 divided by, that's going to be 25, right? No, 100. 100. No, 10. 10. Yeah. But if I do 0.05, it becomes 100. And if I do 0.005, it becomes 1,000, and so on and so forth. So as your denominator gets smaller and smaller and smaller, getting closer and closer to 0, you see that the values just jump up in size by magnitudes of 10 each time. So the point being is that vertical asymptotes happen because as you get closer and closer to having a denominator of 0, as you get closer and closer to negative 1, your denominator gets smaller and smaller and smaller, which means that the thing gets bigger and bigger and bigger, the overall thing. So vertical asymptotes happen where your function is undefined. Yes.
I'm just, so is the hole, is that like, when you're looking at the graph that it had on there, is that where like the BA and HA like intersect? Is that supposed to be where the hole is?
Nope. The hole for this one would be like something like this. Like that.
Oh,
And so we're going to draft one of these eventually, and you'll see it. But I was going to say something, I forgot about it, but like that was going to add on to that, but I don't remember it now.
so what's the point of having?
So the whole is something that has to be recognized. And so we're going to talk about why it has to be recognized and why it happens now. So I hope everyone's okay with that. Like the vertical asymptotes, they happen where the denominator equals 0. But holes happen if a factor gets completely canceled out. So why do I have to learn about rational, like these removable discontinuities? Why do I have to learn another thing? Well, it's because I said so, right? No, it has to do with how the canceling works. So my regular 126 students, they don't go over rational expressions because we have already talked about it. We just talked about this. Remember that if you have, let's just say for the sake of an argument, x squared plus 8x minus 9 over x squared minus 2, or x squared minus 1, that factors to x plus 9 times x minus 1 over x plus 1 times x minus 1. And then these cancel. But there's that thing that we frequently don't write, and that's saying provided x minus 1 does not equal 0, i.e., x does not equal 1. So we learned just about this not yesterday, but on Monday, saying that the reason is that we have to write that technically. That's going on in the background. And so this is another thing to think about. So because these are equal signs in here, we are saying that these expressions, i.e., this expression right here and this expression right here, they're connected by equal signs. So we're saying that these two things are equal. These expressions, this one and this one, are equal. But they're only equal up to a point. This means that for any value of x, except for that pesky x equals -1, or x equals 1, excuse me, they're the same. You plug in 5 into both of those expressions, I guarantee you'll get the same number. You plug in 0 into both those expressions, you'll get the same number. You plug in pi into both expressions, you will get the exact same number. So that is to say, in particular, if we plug in values really, really, really close to that pesky value, we get the same outputs. We get the same number. So for example, at x equals 0.9, we'll get 0.9 squared plus 8 times 0.9 minus 9 divided by 0.9 squared minus 1, and that equals 5.21 dot, 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 on and on forever. And if I plug it into the simplified version, I'll get 0.9 plus 9 divided by 0.9 plus 1. Guess what? It equals the exact same thing. Same number. So these two expressions are equal to each other for everything except for one. One is the problem. Because as soon as I plug in 1 in the left-hand side, I get 0 over 0, which doesn't exist. It's indeterminate. And then, but if I plug it into the other one, I do get a value. So why am I even doing this? Why am I mentioning this? So that is to say, I could do this with any number close to 1. I could do 0.99. I could do 0.9999999. I could do even more. I could do 1.000001. And each time, the two numbers will agree. The two values will be the same because everywhere except for 1, they're the same. And that is to say, the simplified expression, this one right here, which we can plug in 1 into because it exists at 1, this one doesn't exist at 1. This one does. What this is trying to tell us is that the simplified expression tells us what the value should be at x equals 1. They are equal to each other everywhere except for that 1. So naturally, it would mean that as we get closer and closer and closer together to that pesky value, that's what the value should be. So this is what we actually call a limit. And that's what's going to get further explained in calculus. But suffice it to say that the simplified version tells you what the value should be if it were to exist there. Does that make sense? No, it doesn't. That's okay. Thank you for agreeing. I thank you for disagreeing. Let me think of a different way to explain it, because this is a cool thing, in my opinion. I'd like us to know why it's true. So let's go from the top again And let's explain, yeah, JT.
Okay, so you're saying it has to be, because I was confused when you're doing 0.9. Or is it you're doing 0.9 because it has to be under one?
Or like,
Could it be above one?
yeah, so, or could do,
That's just it crossed out x minus. right?
yeah,
Okay.
yeah.
So if, even if it was a different equation, but there's two that you cross out that are the same,
Mhm,
it's whatever that is like that pesky number.
mhm.
Okay,
Exactly right.
okay.
So to recap one more time, because I think this is good for like if we can understand it, then we can apply it. So I hope we're all okay with the fact that we're saying that these things are equal so long as x isn't equal to 1. No matter what I plug into this thing and this thing, they'll be the same number because they're equal to each other. It's just at 1 that they have issues. Because if I plug in 1 into this, I will get 5. Whereas if I plug in 1 into this, I will get 0 over 0, which is indeterminate. It doesn't exist. So, in particular, since they are equal everywhere except for that 1, that means that I can plug in whatever number I want into it besides 1, and it will give me the same value. So in particular, I'll choose numbers that are incredibly close to 1. Whether it be from above or below is irrelevant. If I plug in 0.9 or 1.1 or 0.99 or 1.01, 0.9999999 or 1.00001, no matter what happens, they'll always give me the same number. So in particular, what that's telling us is that I can get really, really, really close to 1 and they're equal to each other. So this thing is telling me what this value should be at 1. What I should have, but I cannot get. That's what it's trying to say, is that the simplified version says what the expression should be if it could be plugged in. And another point that I was trying to make here. What I was going to say. Say it. Another way to explain it. Like, oh well. All right. So, oh, that was what I was going to say. That there it is. There's that thought. These are the same functions. So if I graph them, they gave me the same function. Except they don't exactly give me the same function because of that hole. No matter what, like, so remember, at the end of the day, this is a function f of x right here. And so when I plug in an x value, I get a y value. Plug in another x value, get another y value. But because they're the same thing, if I plug in that same x value into this version, I get the same y value. So reason would suggest that if I plug in 1 into this, if I plug in 1 into this version, I should get what this would be at 1. That's what's going on here, is that the simplified version tells me what it should be at 1. In the same fashion, going back to our previous example here, plugging in -3 into this expression tells me what this function should be at -3, but can't be because you get 0 over 0 when I plug in -3. Let's do an example so we can get further into it. This one here, find the vertical asymptotes of the functions, and if there's a removable discontinuity or a hole, find its location. So I'm going to factor it this time, and this thing factors nicely to, okay, so up on top, that's going to be x plus 3 times x plus 5. And down in the denominator, there's a common factor of 7 that can be pulled out front. And then it's x squared plus 2x minus 35, which factors to, yep, 7 and 5. So x plus 3 times x plus 5 up top. And then down the bottom, 7 times x plus 7 times x minus 5. right? So the good news is nothing cancels. So no cancelizations, no cancels, no holes. Shia LaBeouf would be very upset. Great movie. Love that.
So
Ah,
either one.
that song just it was great. It was great music. You keep digging. And that seems like a very apt statement for this. I'm tired of this, Grandpa. I don't want to do any more rational functions. That's too damn bad, everybody. We got to do them. Okay, so no cancelizations, so no holes. So the VAs will have so this will just have VAs. The VAs where the new denominator equals 0. That's why I said new in quotation marks, because this new denominator is the old denominator. There's nothing new happen, like there's nothing new about it, but sometimes it becomes new. And so 7 times x plus 7 times x minus 5 equals 0. That gives me x equals -7 and 5 as the answers. 0 is not one of them because that's not a 7x. That's just a 7. So by the zero product rule, either 7 equals 0, which is ridiculous, or x plus 7 is equal to 0. That gives me the -7, or x minus 5 is equal to 0. That's where I get the 5. Good. Those are my VAs. Next one, we're going to factor it. In the interest of time, I'm going to factor it for us. This comes to x times x plus 5 times x minus 5 divided by x times x minus 2 times x minus 8. And so the x values get canceled out completely. So it becomes x plus 5 times x minus 5, all divided by x minus 2 times x minus 8. Now, because x got completely canceled out, that means that the original version of the equation would get 0 over 0 once you plug in 0. If you plug in 0 into it, you get 0 over 0, which is indeterminate. There's no way to determine what it is, but we can get the idea of what it is by plugging it into the simplified expression. So I'm going to mention this. This is saying there's going to be a hole at x equals 0. Y value of hole will come from the new from simplified version. That is to say, at x equals 0, we get 0 plus 5 times 0 minus 5 over 0 minus 2 times 0 minus 8, which is -25 over -25 over 16. So we have a hole. Oh, I wrote that very quickly, so I'm going to take a second. Because the x value got completely canceled out, there's going to be a hole where that, like there's going to be a hole at x equals 0, where that factor equals 0, but it's just x, so it's x equals 0. And then to find the corresponding y value, we'll plug it into the simplified version to find out where it should be. Because those two functions are equal to each other everywhere, so the simplified version should tell us where every value should be, including the one where it doesn't exist. So there's a hole at 0, -25/16. And then we've got the VAs. The VAs will happen where the denominator equals 0. The new denominator equals 0. VAs You've got x minus 2 times x minus 8 equaling 0. That gives me two vertical asymptotes, x equals 2 and x equals 8. So we got vertical asymptotes at 2 and 8, at x equals 2 and x equals 8, and we have a hole at 0, negative 25/16. That's how you, oh yes, JT.
Well, it's zero, why can you explain that?
Why there's a hole at 0? So it's wherever the factor equals 0. So in this case, where does x equal 0? At x equals 0. If this had been if it had been x minus 3 times x minus 5 times x plus 5 over x minus 3 times x minus 2 times x minus 8, those would cancel and there'd be a hole at x equals 3. That make sense? So if this was, and then to drive the point home, if this was 17, there'd be a hole at x equals 17, and so on and so forth.
So it's just never matching.
Yes. If there's ever a matching factor that cancels out, there will be a hole wherever that factor would equal 0.
Okay. That makes
What if it's pulled out like 2x on that? Like where the x's got canceled, but it was just 2x. Like, it's still at 0.
If this was a 2x here, then the x would still cancel out. The 2 is just a separate piece, so it doesn't matter. It doesn't play a role. The strange situation that happens is what if this was instead, what if this was x squared up top here? What would that be? So would it be a vertical asymptote? Would it be a hole? It's hard to tell. That's a situation that's a very interesting one. There'll still be a hole because it'll be a place where the function doesn't exist. But it's a weird situation. And then the other question would be, what if it's down here? What if it's an x squared down there? The factor doesn't completely cancel, so there's a vertical asymptote. But don't worry about that. That's a weird situation that we won't see, but it is a cool situation. Any other questions? All right. And we will be tying this all together. We'll be doing plenty of practice with this. So like we will get more practice with it as we go along. But if those ones seem intimidating, the good news is that horizontal asymptotes are much nicer. Horizontal asymptotes are great because there's no algebra that's needed, no algebra whatsoever. Horizontal asymptotes deal with end behavior, just like with polynomials having end behavior, right? So with polynomials, all you need to do is look at the polynomial's leading terms in the numerator and the denominator this time. So if the degree of the numerator is smaller than the degree of the denominator, then there will be a horizontal asymptote at y equals 0. So looking at this function here, it's degree 1 over degree 8. Which implies that there's a horizontal asymptote at y equals 0. And we'll explain why in just a moment. Once we get all the rules, we'll explain why. But if the degree of your numerator is smaller, then you will have a horizontal asymptote at 0, at y equals 0. If the degree of the numerator and the degree of the denominator are the same, then there is a horizontal asymptote at y equals, quote unquote, the ratio of leading coefficients. Ratio of leading coefficients. As a reminder, a ratio in a mathematical standpoint is a fraction. Any fraction is a ratio between two things. You can think of it as any ratio can be thought of as a fraction between two numbers, two quantities. So looking at this one, it's degree 5 to degree 5. They're both degree 5. And so we look at the leading coefficients to determine that there's an HA at y equals 17 thirds. The leading coefficient of the numerator is 17. The leading coefficient, leading coefficient of the denominator is 3. And since they have the same degree, there's a horizontal asymptote at the ratio of those two leading coefficients, 17 over 3. If that was a negative 3x to the fifth, the HA would be at 17 over negative 3. And then last but not least, if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. So looking at this example that's provided, it's a degree 4 over a degree 2. So there's no HA. So if the degree of the numerator is smaller, you have a horizontal asymptote at y equals 0. If not, if they're the same, you have an HA at the ratio of leading coefficients. And then if the degree of the numerator is larger, then there's no HA. So why? Why is that the case? And the key thing is to remember, just like with end behavior is dealing with numbers that are really, really, really large. Whether it be positive or negative is irrelevant. And so I looked at this example in particular. With x to the 6th, this one will have an HA at y equals 1/12. And so the intuition is, pick a number that's really large, 10,000. That's really large for us, but like in the grand scheme of things, if we're talking about end behavior, if we're talking about infinity, 10,000 is chump change. But either way, if you plug in 10,000, x to the 6th becomes 10. I think that's several trillions, or a trillion. Like it's a very, very large number. That's 24 zeros. Whereas x to the 4th is only 1 times 10 to the 16th. So that means that x to the 6th is 10 to the 8th larger. So we're talking 100 million times larger than x to the 4th. So, and that's the same, and it's 10 to the 24th times bigger than 10. And x to the 2nd power, it's going to be 10 to the, that's 10 to the, it'll be 10 times, it'll be 10 to the 16th times larger. And so basically all the other stuff does not matter. All the other stuff, so all you're looking at is the leading coefficients. And so these are going to increase at the same rate. All this other stuff doesn't really matter. And so all you really got is 10 billion over 12 billion, which reduces down to 1/12. When you plug in a trillion, you get 1 trillion over 12 trillion, which reduces down to 1/12. If you plug in a trillion trillions, you get trillion over 12 trillion trillions, and it reduces back down to 1/12. Versus this, when you plug in 10 trillion, this is just 10 trillion, but this is 10 trillion to the 8th. It's so much larger that the denominator basically like dominates it, and it goes to 0. We'll talk about we're past time at this point. We'll pick this up next time and recap it and go over this stuff. If you have any questions, please feel free to email me. Our homework for 2.5 will be extended along with the quiz, because the quiz goes over 2.5. So don't fret on those ones, but do finish 0.8. We did finish 0.8. So if you have any questions, feel free to email me. Otherwise, have a great rest of your day. Have a great weekend. Avoid the doom scrolling. Avoid social media. Have a great rest of your day. Say what? Technically, yes. Yes. Thanks, you as well.